Welcome to Lecture 1 of Chapter 3, Research Design for Program Evaluations. The core of evaluation is research design. What is research design? Research design refers to the model or models that we develop to guide the construction of the comparisons that we're going to make to help us answer the questions underlying any given evaluation. Principal among research designs, and the one that's considered by many evaluators to be the benchmark for isolating the causal linkages between a program and the observed outcomes, is the Randomized Control Trial, or RCT, design. Although neither the textbook nor I wishes you to believe that the RCTs are the gold standard of research design, it is clear that the logic of experimental designs is intended to directly address threats to internal validity, a key issue if we are interested in establishing whether a program caused the outcomes we observed. As I said, research design refers to the model or models that we develop to guide the construction of the comparisons that facilitate the answering of questions that underpin any given evaluation. Major types of designs include experimental designs, or RCTs, quasi-experimental designs, and non-experimental research designs. All three of these are used in program evaluations. In any given evaluation, more than one design is typically used. Of primary interest, of course, is whether or not the program caused the observed outcomes. So because we're focusing on program effectiveness in this class, our discussions of research designs will concentrate on the ways that designs facilitate or impede our ability to answer these two questions. Did the program cause the outcomes we measured? And was the program the only cause of the outcomes we've measured? Experimental designs originated where it was essential to eliminate any factors other than a planned intervention to see what the impacts of that intervention were. On the screen is an example of a diagram often used in discussions of experimental designs, this one coming from the field of agriculture. Figure 3.2. The rows in this chart refer to different experimental conditions. The X's in the chart refer to experimental treatments, or what we would refer to as the program itself, or a component of the program. The O's refer to observations at a given point in time. O1 refers to outcomes in the experimental treatment. In other words, outcomes produced with the program in effect. These then are compared to outcomes in a control group, shown as O2 in the figure. These are observed outcomes without the program in effect. Note that O1 and O2 are observations taken at the same point in time. In figures of this sort, this is usually indicated by showing one above the other. Figure 3-3 shows a more complicated design in which each cell of the diagram contains a different set of experimental conditions. For example, in the upper left cell of the table, two sets of seeds have been planted. Both sets, however, are in land that is not next to an experimental plot, or in which there's land unplanted next to the experimental plot, and in which no fertilizer has been used. In the upper right-hand cell, again, two sets of seeds have been planted, the experimental seed and the standard seed. Here, there is unplanted land next to the experimental plot, but no fertilizer has been used. At the bottom left, two sets of seeds. There is no unplanted land next to the experimental plot, but fertilizer has been used. And finally, in the bottom right-hand cell, two sets of seeds. There is unplanted land next to the experimental plot, and fertilizer has been used. Within each cell, then, outcomes for the experimental seed are compared to outcomes for a standard seed. So one winds up making 4 sets of comparisons. As shown in Figure 3-4, the strength of experimental designs is the ability to eliminate plausible rival hypotheses. In other words, other explanations for the observed outcomes. Through careful control over experimental conditions, researchers are able to conclude that any changes in outcomes from one time to another, or any differences in outcomes across 2 or more groups, are attributable to the experimental treatment. In other words, they are attributable to the program. Take note of what I just said. Researchers are able to conclude that any changes in outcomes from one time to another, or any differences in outcomes across 2 or more groups, are attributable to the experimental treatment. 2 different situations. One across time, one across groups. This is illustrated in Table 3-1. People often believe that the heart of experimental logic is the pre-post aspect of data collection, collecting data before a treatment and after the treatment. This is clearly seen in the classical design portrayed at the top of the table. But this is not the heart of experimental logic. Instead, the heart of experimental logic is in the random assignment of subjects to either the treatment condition or the control group. This is indicated by the R in the designs shown in the figure. Experimental designs have become the standard for medical trials. For example, new drugs are tested in double-blind RCTs, wherein neither the patients nor the experiments know who is receiving what treatments. Efforts such as these are made to protect the internal validity of the study. Of course, no design is perfect, and there are problems with experimental designs. The logic of experiments, that is, the need to account for, control, or eliminate factors other than the program when we are assessing program effectiveness, is broadly applicable to program evaluations, regardless of whether we're in a position to use experimental or even quasi-experimental designs. Historically, program evaluations depended heavily on experimental designs. This was especially true in the 1960s and 1970s. However, there are a number of problems. The impracticality of large-scale experiments, which can be very difficult to administer and very costly. The problems with interpreting experimental results under multiple conditions. And finally, there are ethical concerns about controlling and in some cases withholding treatments. Taken together, these diminish the collective enthusiasm for experiments as a way to evaluate programs. Nevertheless, RCTs are still a key part of what evaluators do. There's been a resurgence in interest in RCTs as a result of evaluation requirements by some departments in the U.S. federal government. In the textbook, the description of the Elmira Nurse Home Visitation Program is intended to illustrate the process of designing and implementing an RCT experiment. The nurse home visitation research has been going on for over 25 years in the United States and has been focused on the question of whether systematic home visits by registered nurses to the homes of first-time pregnant mothers A. reduces the incidence of poor pregnancy outcomes and subsequent neonatal health and development problems, and B. enhances the mother's own prospects of educational and employment improvements. The experiments have been conducted in 3 cities: Elmira, New York, Memphis, Tennessee, nearby to the Jonesboro campus, and most recently in Denver, Colorado. The findings suggest that nurse home visits and even visits by non-nurse paraprofessionals cause a range of positive outcomes. Because each experiment had one or more control groups that had been randomly assigned to treatment or control conditions, the results are generally viewed as being robust. Together, they are an impressive research program that is intended to influence public policy. You have reached the end of Lecture 1, Introduction to Research Designs. When you're ready, please proceed to Lecture 2, Establishing Validity in Research Designs.